Hey, what's up, everyone? Welcome back to SSP Diving. I just want to thank you all for the incredible questions on the last video. If you're new to this channel, my name is Sakeli. I'm a commercial diver with thousands of dives under my belt. I've also appeared on Discovery Channel working with saltwater crocodiles in Papua New Guinea. I personally had communications with OceanGate before the tragic incident, and since they're also based in the same city as me, I often followed their expeditions through local news updates and social media. As a maritime professional, this gives me a unique perspective on subsea conditions that's going to be different than your typical engineering videos that you might find on YouTube. My goal here is just to break down all these complex topics and terms and present them in a simple manner for you guys that everyone can understand. Like many of you, I've been fascinated by this unfortunate tragedy, so I'm just here to try and piece everything together as information is released. We now have some updated information to share regarding the construction of the carbon fiber hull and acoustic monitoring systems. Thank you to the viewers who pointed out some additional details. In the previous video, I mentioned if it gets over 100 likes, I'll start a series. And well, that video hit over 1,000 likes so far, and it's time to continue our investigation into this Ocean Titan tragedy. Okay, so some of you guys may remember Bill Nye the Science Guy. Well, this is a demonstration that I saw when I was a kid, and it always stuck with me. So inside of this barrel, there's just a little bit of water here at the bottom, and there's a small opening here at the top. So all of that water is boiling. It's creating a lot of steam. It's creating a lot of internal pressure. So he's going to go ahead and cap off that barrel and place it inside of this ice water. Now, as you can imagine, what he has here is a propane heater. So he's heating up inside of this 55-gallon steel drum. That pressure is going to try and equalize to the temperature around it. So when that barrel cools, it's going to essentially implode, and we're going to get an idea of what happens during an implosion.
The ordinary oil, 55 gallons.
So here you can see the steam coming out.
About a liter of water in the bottom of the barrel, heated by the propane. Here, what I will do now is turn the propane off. The propane turning off. Now, John, I'm going to put this in the bung hole. This is what, John?
That's good.
That's a bung.
That's the most popular phrase in my house, I can tell you that.
The bung there. Now, John, it looks like a bung wrench.
Yeah, but we're always coming over to your house asking for the bung wrench.
Sure they are, Mike.
Yeah.
Sure they are. It looks like an ordinary bung wrench, John, but when we put the yellow and black tape on it, that is a bung wrench of science.
All right.
All right, Bill.
Into the ice water it's going to go.
Okay, so now he's going to lower this into the ice water.
It's better, better if you move quickly. You can hear the ends. The ends are collapsing.
And he's going to roll it around there to try and cool down the surface of this barrel.
I don't know, John.
So just watch closely here.
We did the classic demonstration.
Do you see how quick that happened? That's an example of an implosion. I've got one more for you guys. Okay, so I've got one more demonstration here for you guys. They're doing the same thing. I like this one a little bit better. The video quality is a little bit easier to see this implosion. Okay, so now they're putting it here into the ice water. And it's actually taking a second here, so they actually have to try and expedite the process, put some ice on top of it. So listen closely and look very closely. You guys might miss it. Watch very closely. You guys might miss this. Listen very closely for any creaking. So turn your volume up. I know I got somebody. I know I got somebody. So let's just go ahead and watch that one more time so we can get a grasp on how instantaneous an implosion would be. That quick. Okay, so we did dive into the construction of the hull a little bit. I just want to do a quick review on everything. So this is their LARS, launch and recovery system, and there was numerous issues with that in itself.
The most difficult and expensive aspect of submersible operations is the launch and recovery of the vehicle. And most deep diving subs have dedicated ships with very expensive launch and retrieval systems. We made our system on the backs of the work that was done at the Hawaii Undersea Research Lab, and we launched the sub on the platform that is towed behind the mothership. and then the submersible command module leaves the platform, does its mission, comes back to the submersible, mates underwater to the platform, and then is brought to the surface.
Okay, so does that make sense to everyone? So this barge right here, essentially this is a floodable barge. So this barge has 4 separate chambers in it, and these tanks right here are all filled with air. So when they're heading out to the dive site, this pontoon right here, essentially it's similar to just like a pontoon boat that you guys would see. So the hull is normal. It's filled with air just like it should be. They'll tow it out to the dive site, and then when it's time to launch the submersible, they'll actually flood the entire barge here, and then the submersible can go detach and go do its dive, come back. One of the questions that I had was, so if this is going to detach underwater, well, how do you know where this is when you come back? Well, a couple different methods here. So when that barge is flooded, here you can actually see the tail cone of that submersible. It's going to have these buoys here that are actually not only marking it, but sort of keeping it afloat. I believe that the material here that they used is actually aluminum construction, which is pretty light. Now, so these volume tanks are actually filled with air. The submersible will come back. These volume tanks will pump air into the hull, and then it'll be on the surface. Now, that's how it's supposed to work in theory, but the issue that I'm seeing here, it's actually very narrow, and not only that, but it's going to be very top heavy. So you're going to have this heavy submersible, and remember how he was saying that usually you need a heavy crane to lift these submersibles. That should give you guys an idea of how much weight is going to be on top of this pontoon here. Now, I'm calling it a pontoon as in a pontoon boat or a pontoon barge, just for the lack of a better term here, because typically you can actually have something somewhat narrow like this, like a pontoon boat, but the pontoons are going to be on the outsides or outside edge. But it appears to me that the entire barge itself, the entire hull fills up with water. Now, I may be wrong on that, but when the entire barge, entire hull is filling up with air, and you have a top-heavy submersible on top of it, along with all the volume tanks and other hardware and everything like that, well, it's going to want to teeter-totter. And so that's exactly what was happening, and we'll see some of that in these photos here, is that they were trying to get it up to the surface. But not only is it top heavy, but I'm not sure where the exhaust was for the water to escape. But it's possible that once it gets tipped up, well, there's going to be water that's trapped down at the bottom, and no matter how much air you try to force in there, you can't get the water out. So that may be one of the issues and why this thing was tipping up. And here you can actually see it slightly tipping when they are launching it here. And this is in their promotional video, right? Okay, so here's some more information presented by the Coast Guard with their launch and recovery system. So it was built by Everest Marine, who I'm actually familiar with, because they're a Seattle company as well. Now, it was built in 2017. The length on this was 38 foot long, 16 foot beam. So the beam is the width of this. So it was only 16 feet wide, which, like I said, that is rather narrow, and it had essentially a 3.5 foot depth, which is, for that, it's somewhat tall. It's somewhat tall. Now, it says here that there were 4 separate hull compartments that would be manipulated to flood to sink the platform about 10 meters or 30 feet below the surface. That allows for the Titan to depart and arrive underwater under the surface. So, yeah, we just went over that. Those compartments would then be filled with air from 4 air receivers, which are these guys here on the LARS, to raise the platform. This action is completed by the platform operator, who is stationed above in a small vessel. So I think that's what this is right here. I believe this right here is going to be a small compressor that they can take out there. I could be wrong there, but I think that's what that is. If not, it's maybe some sort of emergency transponder system. Okay, so in the last video, we actually went over the construction of the carbon fiber hull. Well, I want to touch back on that. There's some information that the viewers had pointed out, which I need to address so we can help paint a better picture here of the carbon fiber hull design. So we know that the carbon fiber hull was wrapped in a cylindrical design. Now, I had thought that the entire hull was wrapped in that fashion, but we're going to look at some details here in the report. Okay, so it says here in the NTSB report that the build sequence consisted of 2 cylindrical plies. So cylindrical meaning like this. So they would do 2 wraps essentially laid down with tension. So this is going to be under tension. These are going to be tight cylindrical wraps, followed by 1 longitudinal ply until they would reach 1-inch thickness. So it wasn't just linear cylindrical wraps. They would do 2 wraps that were tensioned tight, followed by 1 wrap that was longitudinal, and they would continue doing that until they reached 1-inch thickness. Once they got to the 1-inch thickness, then they would take this and grind down any deformities, as we discussed last time, any wrinkles, any waves, which, in my opinion, if you have something, I'm not an engineer, if you have something that is wrapped tightly around under tension and then you cut it, I think that would introduce weakness and failure points. Be aware of something here. So they would build it up 1 inch with carbon fiber, right? And then they would add an adhesive after grinding this down smooth and cutting those layers. They would add adhesive and then they would cure it. And then they would do the next layer of 1-inch wrap. Well, why is this important? So they're talking about the autoclave. So the autoclave, I guess, is where they would take this to cure the adhesive before beginning the next layer. Why is that important? Well, where they had the carbon fiber wrapped was here at the Electro Impact Facility in Mukilteo. And they then had to take the hole, drive it to Janicki Industries in Hamilton, Washington. I don't even know where Hamilton is. So let me pull this up for you guys real quick. Let's see how long of a drive that was. Okay, so I'm recording this on a Sunday evening with no traffic, and with no traffic, we're looking at 1 hour and 8 minutes. So I'm not sure how exactly this was transported. They didn't really detail that in any of the reports, but it's going to take 1 hour and 10 minutes to get from the carbon fiber location to the autoclave curing location, which is surprising. I thought this was all done in the same facility, but apparently they would take the hole, somehow they would lift it, load it, secure it, drive it down these bumpy roads all the way down to the autoclave center. So yeah, I don't know why I'm so surprised by that, but you have to factor in 2 hours of road time. It doesn't sound like this was a quick process because it says that autoclave curing was performed by Janicki Industries in Hamilton, Washington. Whole production took place between November 2020 and January 2021. So this happened over the course of a few months, really. This wasn't like a quick process. This took time. So they did take their time making this hole. So I'm just not sure if there would be any introduction to moisture. I'm not sure how you would prevent that when you're driving this thing down the road 1 hour each way. Yeah, just shocking. I was actually extremely surprised to hear that. But you know, at the same time, not surprised. The amount of negligence here is pretty astounding. As we continue to piece things together here, one thing I wanted to point out was the forward dome and the viewport here. So I think when they always mention the viewport, we always visualize it as a window because that's what we're used to. So we visualize this as being one big window. You can only see the thickness of it right here, but it's actually tapered here so it fits inside of this viewport dome. So here's a better look at that acrylic viewport. I don't know about you guys, but I pictured it, but I imagine this being more sort of a window, like a thick window that was bolted to the outside. This actually is tapered here on the edges so it can fit inside of that forward dome, which we'll see here in just a second. This is during the machining process. So they're actually machining this dome and it's going to slide inside of there. This was from OceanGate in 2017. The forward titanium dome and acrylic viewport have arrived. The 23-inch viewport is the largest of any manned submersible capable of reaching 4,000 meters. Well, I think we're all kind of wondering if potentially if this was a weak point. I thought the design was slightly different. Actually, after seeing this, I feel a little bit more confident in that acrylic viewport. But at the same time, I'm not an engineer, so I'm not sure exactly how this would react at those depths. So this is not the viewport here. This is just a piece of plexiglass over that viewport cavity. And here, this is a CAD drawing from Vegas Cycling Freak channel. His channel is very helpful when I needed to try and illustrate this a little bit better for you guys. So it actually sits inside of that dome and then is held in by a retention ring. And there's a close-up of it, so you can see where those tapers were that we were looking at. So it actually sits inside of this dome here at Viewport, and then this blue liner here is actually a ring that helps secure it in place. At least it's tapered and it has a large mating surface. Stockton Rush did also sort of proudly claim that the acrylic Viewport would actually hear a ton of crackling. Essentially, you would hear this thing breaking before it failed. He seemed pretty proud of that, but to me, if something is going to be crackling at those depths, you're not going to have much of a warning. So I wonder if it's possible that this actually was the failure point, if it ended up being sort of brittle. I did find some receipts when they purchased this, and it was about $10,000 to have this acrylic Viewport manufactured and shipped over to them in 2017. So this year was actually extremely eye-opening as well. So it says the 2022 expedition from June 14th to July 25th. So it was 13 dives, 7 were successful. Now, during this, so they had 48 equipment issues. Okay, you know, whatever. We know that it has its issues, right? Well, it says that upon completion, Titan was stored at a shoreside facility in the parking lot along the dock without protection from the elements, uncovered. And this is in Newfoundland. So this was from July 26, 2022 to February 6th. So you can see snow on the ground here. You can see that it's uncovered. It was stored uncovered. Now we know that this white layer here is not waterproof. Okay, so this is separate from the carbon fiber hull. It's attached to the frame and it helps prevent the hull from abrasion damage. It allows for instruments to be attached. It provides the hull from protection from being bumped, from anything bumping up against it. This tail cone and this white section, this is not waterproof. So this was left outside in the elements, exposed to freezing temperatures. It was exposed to UV rays. It was exposed to rain, moisture, who knows what other elements. So that was very, very shocking as well to see. So here we're looking at the completion of the carbon fiber hull once it was completed being wrapped. It's also only being supported on one side right now, which to me is a little bit concerning given the weight of this, and it's only resting on 2 dollies. So even upon the completion of the carbon fiber wrap, you can actually see all these wrinkles in the carbon fiber. Well, remember when Stockton Rush was talking about his Rhino Liner?
Get the aft dome here. This is another 3 1/4 inch thick titanium dome, bolted to another titanium piece glued to the carbon fiber. Carbon fiber is coated with Rhino Liner, which is
Rhino Liner. So we went over that in the previous video. We talked about that, but here, even in this video, where they're on a mission and they are going to dive this vessel, you could see the wrinkles here, all these wrinkles. So they just painted over those wrinkles. Now, Rhino Liner is known for being very durable. Obviously, they use it in truck beds. It's known for having great abrasion resistance. Now, they have used it on boats, but it's mostly going to be on the hulls or on the gunnels. Okay, so he seemed very proud to share that with us. Well, if you just type in Rhino Liner Military, Rhino Linings is a company that provides protective coatings for military use, including blast mitigation, force protection, anti-terrorism technology, corrosion resistance, abrasion resistance, impact resistance. I think you would have a hard time trying to find anything that mentions use for submersibles, for submerged use, prolonged submerged use. So I just wonder how the Rhino Liner may have infected the integrity. So here you can clearly see all of these wrinkles here, and you can even see, I don't know what this is here, but can you see how rough that surface is there? Maybe we can get some more information on that, but that literally, they're on an expedition. This is ready to launch right now. And look at all these long wrinkles that you can see in the carbon fiber. So I wonder, so even if the Rhino Liner is not permeable at that depth, to my understanding, it's going to add an additional difference in compression rates. So and if it's glued to the carbon fiber strands, well, I think what's going to happen is if you have like one of these wrinkles here, I think that there's actually going to be maybe air or porosity behind those wrinkles still. So that to me feels like, I mean, using truck bed liner to go down to the Titanic, I mean, I think we all have the common sense to say no thanks. But yeah, that's pretty crazy. So, I mean, I didn't realize you could still see all these wrinkles. I thought they would have at least smoothed that out or something, but yeah, pretty crazy stuff. Okay, so the last thing I want to touch on here with you guys are the acoustic monitoring systems. So I misinterpreted some of the data from the previous video. Again, thanks to our viewers for pointing that out. So they had 8 different locations throughout the hull. They had acoustic listening devices, but they also had hoop strain gauges. So that's what some of the data was. And so they had different locations for these gauges. So they had them set here a few inches inside of each end of the hull. They had them on each dome as well. And then they had them in numerous locations throughout the hull. So this is going to get a little bit confusing here, but just stick with me. So as I mentioned, so there's 8 different locations for these strain gauges. Okay, so not only did they have acoustic sensors that can pick up sound, but they also had strain gauges. So the strain gauge is going to essentially, if there's a compression of the hull, it's going to measure that, and it's going to give us that reading in an electrical output. But that's going to get a little bit too confusing. So we're not going to go into the millivolts and all that. Okay, so as an example here, they are applying a strain gauge to the outside of a pop can. So I want you to think about the strain gauge similarly being applied to the OceanGate Titan. It's going to measure the pressure on the wall of the hull. Here with the pop can, it's going to give 2 different outputs, whether the pop can is pressurized and it's full, versus when you open it, it's going to give you a completely different reading. So essentially that is what the strain gauges are meant for on the Titan. So before we move on here, let's just go over the locations. So you have the acoustic sensors here, strain gauges here. So the Ford titanium dome, there was no acoustic sensors. They didn't have any on there. Now they did have them for the strain gauges. Composite hull, so 3 inches or 4 inches back from the forward end, and then 100 degrees clockwise from the top, so 110 degrees clockwise from the top. And then they also had it in the middle, so mid-span, so these were located in the middle of the hull, again in the middle of the hull, again in the middle of the hull. These are just going to be at different location. So on the aft end of the hull, on the stern end of the hull, just 3 or 4 inches in, they had a couple of sensors there as well. Okay, so the dives that they're going over here, these are dives 75, 76, and then 79 through 83. For whatever reason, I don't know if they didn't have the data for 77 and 78. For reference, the tragedy took place on dive 87. So these are dives leading up to that, just a handful of dives before this incident. Change in strain response of composite hull. So on July 15th, 2022, the Titan dove to the Titanic, reaching a depth of 38,000 meters. This is on dive 80. Dive 80, okay? Shortly after resurfacing, an audible loud bang was heard, according to the dive log. Acoustic emission and strain data collected by real-time monitoring system, that's what they're calling the RTM, real-time monitoring system, was processed by OceanGate personnel after the dive, which is their typical procedure. So this says, while at maximum depth there was time-dependent reduction in hoop. Now the hoop strain gauge, I guess what a hoop strain gauge essentially is what I was being explained, is that it measures not just one area, but I think it it measures the entire circumference of one position. So that's why they have those multiple sensor clusters together. So it says, while at maximum depth, there was a time-dependent reduction in hoop and longitudinal strain gauge output. When the vessel returned to the surface, the strain gauge voltage outputs were lower than they were at the start of the dive. I'm not sure if exactly what that means. To me, it seems like there was possibly stored energy inside here, because it says then there was a burst of acoustic activity shortly after surfacing, approximately between 15:15 and 15:30 Newfoundland time. So it says here, so this is after the fact, changes were observed in the initial strain response of the hull following dive 80. Figure 28 shows the variation in hoop strain gauge output with ocean depth for Group 4 on dive 80 prior to the audible event, which occurred after surfacing. For visualization purposes, strain gauge output is plotted on the horizontal axis, and ocean depth is plotted on the vertical axis. Okay, so this one right here is figure 27. So this is time plot of channel 2 acoustic activity hoop strain and longitudinal strain from Group 4 for dive 80, 2-hour interval after surfacing. So this is 2 hours after surfacing. I believe this here in the purple is the acoustic activity. This is the loud bang that happened on surface. So there was then a change in hoop strain. So if anyone here can interpret this a little bit better, so the hoop strain, it looks like it was slowly weakening to a point where it released that stored energy. And this purple here is just the sound that we're getting. So we're going to get ambient sound here. This is all most likely ambient pressure, ambient sounds here from the hull. But this here, no mistake about it, this is a loud bang that was recorded. And it appears here that, so this is the hoop strain. I would assume that this is going to be where it should be. And I think that the strain here, it slowly got weakened. You hear the loud bang, and now this is the new floor for the hoop strains. Let me know if I interpreted that wrong, but that seems like it makes sense to me. It seems like this was slowly leading up to something, like something failed. These are the strengths where it was previously, and this is where it's at now. Okay, so this is Dr. Kramer from earlier this week. He's going over the acoustic and strain gauge outputs.
Yeah, so referring to slide 40, when plotted together, one can see that the sudden change in strain gauge readout coincides with the large acoustic event. Some of the gauges showed a change in strain response after dive 80. OceanGate strain data was typically, and perhaps always, plotted as a function of time. The changes in mechanical response are easier to visualize by plotting the strain against dive depth, as shown here for the hoop strain at gauge group 4. Plotting the data in this manner is more akin to a stress strain plot, which is a standard way of visualizing this type of data. For dive 80, prior to the event, the relationship between strain and dive depth was a straight line for both the descent and the ascent. Going backwards in time by 3 dives and comparing dive 80 to an earlier dive 75 reveals no significant change from dive to dive. Moving forward in time and looking at dive 81, the dive immediately after the event, we see a change in the initial strain response of the hull. The next slide focuses on the initial and final 1,000 meters of the dive. The graph on the left shows the hoop strain, and the graph on the right shows the longitudinal strain. Changes in the initial strain response are seen in both directions.
Okay, so just going to pause real quick. So remember, the hoop strain is what's going around. It's measuring the circumference, the change in the circumference. And then longitudinal is measuring change in length.
Furthermore, the changes persist from dive 81 through dive 83, which is the last dive for which we have strain data. So changes in strain response after dive 80 were also seen for the longitudinal strain for gauge group 5 and to a lesser extent for the hoop strain at gauge group 8. Those changes also persisted for dives 82 and 83. There were no apparent changes for groups 3 or 7. Make sure I get my bearings right here. So the acoustic emission response at the forward port side sensor showed a slight initial increase after dive 80 and a fall off afterwards. Here we see the response for dive 80 and its spike in acoustic activity after returning to the surface. Looking at dive 81, there was an increase in acoustic activity during the descent and once again an increase in activity after returning to the surface. Dives 82 and 83 show a trend of the hull becoming quieter with successive dives, as seen here for dive 82. Next slide. And here for dive 83.
So I find it pretty alarming that after that loud bang, now we've been hearing all this creaking, all this cracking, and now all of a sudden, after this loud bang that happened 2 hours after the dive, well, now all of a sudden it's quiet. That to me is a telltale sign there is something obviously wrong with the carbon fiber hull. They should have done an all stop here. They should not have continued diving this vessel.
One note about dive 83, this dive did not take place at the Titanic wreck site and did not go to the same depth as the other dives. According to the dive log, it reached a depth of 2,954 meters. This is the last dive for which acoustic emission and strain data is available.
Isn't that incredible? So after that loud bang, there's 3 more dives that are available where they have the acoustic data. Now we're missing 4 dives where there's no acoustic data available. So we don't know where that data is. It says that that's all that was available to them when they did this investigation. It almost seems like to me after dive 83, there was some information that was intentionally deleted. After hearing this loud bang and before the fatal accident, all of a sudden there's this gap in data where we're starting to see differences in all these strain gauges. That to me is a major red flag. The last thing I want to address here is this presentation from the American Bureau of Shipping. These are pressure hull requirements for passenger submersibles. So ABS, they classify all of our ships, that are carrying shipping containers. Well, they also do that for other vessels, including submersibles. So regarding the OceanGate Titan, they didn't have any involvement with the submersible. It said that they never received a request for classification submitted to ABS. There was also no design review or surveys conducted by them. And we know that, and that's part of some of the regulations or laws that Stockton Rush was trying to skirt by going out to international waters so that they don't have to abide by some of these rules. So we're going to go over this presentation here in another video, but I'm just going to skip to this section where it mentions non-destructive inspection of thick carbon fiber sections, e.g. 5 inches thick like it was here with the Titan, with multiple layers possesses challenges. Ultrasonic examination may not suffice due to lack of penetration of the ultrasonic waves. So with ultrasonic testing, it's most common that they are testing thickness, but also with the waves, I believe they can detect any gaps, any air gaps, any porosity, things of that nature. They say for thick carbon fiber sections, inspection technologies such as X-ray are more effective. Now, from a practical standpoint, from Stockton Rush's point of view, conducting this level of inspection on a periodic basis could be challenging due to the following items. Most likely, one would first need to strip fully the outfitted pressure hull to its bare configuration, which is what I mentioned earlier. So they would have to strip everything down. They would also have to get rid of all the equipment on the inside, as well as any external equipment, and they would have to remove any lining, any insulation, any coverings. So that Rhino Liner, they would have to strip that off in order to get a thorough inspection performed. In the next video, I would sort of like to explore other submersibles and compare them to this one, look at different designs and why this design is inferior to, say, a spherical design or other designs that are proven to work. Now again, you guys, my heart really goes out to all of the victims and everyone that's involved. I personally know some people with OceanGate that worked for them. There were victims that didn't deserve to die like this. There were families that didn't deserve to lose them like this. So this whole thing is very tragic, and we're trying to understand. Like I said, I'm not an engineer, but I am someone who spends a lot of time underwater and in the marine environment, so I can sort of relay this stuff and explain it in a simpler fashion to everyone. So the marine industry is very close-knit. It's a small world. So from anyone from fishermen to divers to captains to people working in submersibles, we're all a very tight-knit group. So when something happens, hits very close to home for all of us. So thank you all very much for watching. Please leave a comment down below with what you would like to see in the upcoming videos. I said I was going to do a series, and we're going to stick to it. So thank you all, and have a great day.